The thing has been hit. The thing since we're live. All right, we have a nice successful clap there. Hey guys, what's going on? Memes here. So today, as yes, Dan, it is totally that crazy. Or hopefully it's crazy enough. We shall see. But hey guys, what's going on? Memes here. So yes, as the title suggests, there's going to be a series of crazy calculations. Now, the terrifying thing is a lot of this stuff, or at least the components, are within the standard and concordance models of modern physics, physics in general. Um, and I'm sure some people have conjectured them, but and occasionally you see an occasional, oh, that's an interesting coinky dink. That's an interesting coinky dink. Okay, and if you're going to do the whole Bayesian reasoning, it's like, all right, we have our priors. What are our priors? The things we knew before that explain what's going on to the best of our ability. Okay, now, again, my dad, God rest his soul, he was an attorney. And he always told me, number one, the truth is the ultimate defense. Number two, you follow the evidence. So, what does the evidence may suggest? And if you got a coincidence, that's cool. And then it happens again. It's like, all right, it's just it's a pretty good coincidence. And it happens again and again, kind of like what are these lines within like these frequency of radiation being emitted from these elements? Seems like there's like a fine structure going on. And again, if it was just for that, you're like, all right, well, maybe that's just a coincidence. And then you needed to calculate like the radius of the electron, and you need to do it to calculate basically the mass of the electron, or at least that we conjecture that, and it seems to get it pretty dang well, or at least the charge. Oh, never mind. I'm making that. I'm confusing charge boundaries there with mass. That's this is why we write things down. Why we write things down, and I even had to pull out. Oh God, was it the video from when I was on? Was it Jeremy the Alien Scientist channel at one point? They had Dr. Salvatore Pison, Mike Perrone, David Chester, a bunch of folks there from like the alt propulsion community and stuff. And it was very interesting because I had to go back and be like, where the hell was this calculation? I'm going through and it's like, no, it's in a saved Wolfram notebook from like last year. I I needed to double check to figure out what the heck equation I did to get the particular thing. Uh, Again, this is why saving is a very cool thing. But yes, I see it. I see it. I understand that. Okay, I gotcha. This thing will notify. See, Jax, I cannot comment on that. All I know is when you have different phone settings and everything, sometimes I'll go in. I'm like, didn't I have this clicked on the browser? And then you click the thing on your phone, and then maybe it works on your phone, maybe it doesn't work on the browser. I don't know. I'm not an app developer, so I can't intelligently comment on this. Many folks would say, I can't intelligently comment on this. That's totally fine. Everyone is entitled to their own opinion. So, as folks are coming in from different parts of the internet, the ex Twitters, the blue skies, I don't even know where the realm of Discord that may be using face scanning technology to, to now enable you to log in. Oh, yes, we're there, my friends. You say goodbye to anonymity on the internet. For the most part. Hashtag not all. Okay. But what we're going to do now is we're going to go through a series of calculating. And don't worry, we're going to keep it simple. We're going to keep it simple. It's literally the links are in the doobly doo below for the stuff we're going over. So if you're ever like, oh my God, I have no idea what he's saying, it's okay. You can totally trust, but verify. You can always verify later, but it's one of those things where you start seeing certain patterns, kind of like, all right, we have this fine structure as we're heating up these different elements and everything. All right, and then it pops up, and then it seems to work in all these other places, and that's what we're going to be going through today, my friends. And a short road trip story about meeting a mad scientist with a mathematical gangster. Yes, it's, you can't make up real life. It's uh, but okay. Is it okay if I erase stuff that we took pictures? Okay. All right. So let's do it. So while we're erasing the board, what the heck am I talking about? Well, like, hey, y'all are getting sneak peeks of stuff that's coming. And we should just start throwing some. We should probably just start throwing these pictures on the monastery Patreon and stuff. So it's we give a little bit more incentive if you want to get a little bit more ahead of what gets actually put out, just because I found, hey, actually, aside from any of the physics or anything, just streaming and finding different like-minded folks or fans of different fandom and stuff. Some of the best conversations happen actually before and after. So people don't always see everything that's going on. Perhaps that's for the best. But other times, it's certain people feel inclined to present themselves in a very particular type of way, and they must do this. And somebody says this word, they have to be that word bad, and blah blah blah. It's a everyone again is entitled to their own opinions, but somehow I feel if somebody doesn't have a camera shoved in their face, they tend to react more positively, or at least in more hostile political environments, we'll say, when you're trying to be a mediating party between two factions that hate each other. I'm just saying, hashtag Boston Strong. But it's a very fun thing. So, like we've done a bunch of previous days, maybe we'll see. We'll do maybe blue, red, and green. There we go. Those are like Christmas-ish colors. Okay. So, like many times before, and I've learned this from Harry Potter, you need to present information at least 3 times or as many times as possible for maximum retention. Okay, so what am I talking about? So we start off, we're just gonna go with our friend Alpha again. All right, we're starting off with our little fish Alpha. Okay. And when you realize that Alpha can simply be expressed as elementary charge over the Planck charge. We throw on our protective brackets. We square the whole dang thing. We get alpha. That's beautiful. Okay. So if we see something like that and you're like, all right, we can use this equivalence, we're adopting a slightly different convention because what are we going to do? We're going to before we had something like this. For example, yesterday we were going over the PB&J conjecture, which I would claim is the tastiest of conjectures. Is it right? I don't know. We're going to have to follow the evidence. Again, looking for group muon collider. All right. So basically, before we were expressing it as, let's do it red because I have different colors in my hands. All right. So in order to try to calculate for the Higgs, here's the equation we were doing before. We inverted it, so we were doing Planck mass, and we were doing it over, we were solving for X, so we would do X kilograms, square the whole dang thing. We multiply it by H bar, which appears to be the missing piece in the puzzle, and then we set it equal to 1 joule second. Okay? Now, again, you can write this in a whole bunch of different ways and everything, but we're leveraging the known 5 digits, 7 digits of error of the Planck mass with the 10 defined digits of H bar, and we set it equal to 1 joule second since we have the relativistic mass of the joule to 10 significant digits because we have 10 significant digits for it. Okay, we're claiming, or at least I'm willing to claim, that this could hold true for A1. Perhaps there's a different geometric factor, maybe like a Giesing constant squared or something to divide in there. It's based upon a previous calculation to get it right within 1 sigma of the current one. This one comes out to be for the Atlas 2023 about 2, maybe 2.5-ish sigma. It's like 0.2 sigma for the CMS current measurement. So again, oh yeah, and some of the first measurements with the error and everything, it was literally at 125.37 GeV. Okay, but you see this, and it's like, all right, well, you could always rewrite this. You could always rewrite this. Well, let's do green because we have another color. Cool. All right, so you could always just rewrite this. That had pointed this out. You could, if we're going to claim that's the mass of the Higgs, then we can just conjecture that's the mass of the Higgs. Putting it over the Planck mass, MP, we're squaring it, and that would be equal to the magnitude of H bar. You can do that out, and I'm like, all right, well, that seems to be a very interesting coincidence. Now, I'm showing you this for later. Number one, it's a pretty thing. Number two is, well, you're gonna see. I think you guys are gonna like it. Um, but the other way you could express this is, and we'll just, oh no, 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 I'm going to express. I have a thing in my mind. I'm doing this for a reason. So I'm trying to look at it like taking the whole Wolfram Feynman method and just be like, look for the simplest parts. What are the simplest parts that we can maintain without having to change the conventions around? And if we have five pieces that we can usually do that with, we just pick the magnitudes of the five pieces and we go from there. Okay. But what I like to do for this guy is we did back to blue. Okay. So we're gonna make the claim that I just okay. So we did the mass of the Higgs over the Planck mass. Okay. Put our handy dandy brackets in. So we're basically doing the same thing as up there. I should put that on that side. I planned it out in my head before. Let's it's because I've started every video with alpha on that side, and I had to run it through going the other way. So we'll just do this. Yeah, yeah. So just yeah, if we're gonna set up a convention, let's actually set up a convention, shall we? All right. Let's m sub h mass of the Higgs over m sub p blank mass. Okay, and we're squaring this, and then we're simply going to claim that it's h bar over joule seconds. Let me make sure that's right. Yep. That's hold on, let me check ahead. Uh yep. Okay. Oh no, no. There is a reason. There is a reason we're getting into this too. And oh hey Mark, good to see you, my friends. But hey, you want to get in the middle of a couple of fractions. Okay. So this is interesting. It's like, all right, so if we take the elementary unit of charge, we divide it by the boundary of charge. Okay. We square the whole dang expression. We get alpha, the fine structure constant. All right, that's pretty cool. All right, but now I'm going to claim the mass of the Higgs divided by the mass boundary, the Planck mass. You square that thing, that's equal to h bar divided by joule seconds. It also makes it computationally easy if you're using a tool like Wolfram Alpha because the magnitude, it can be kind of iffy because now it's like it will give you the magnitude, but then if you try to run on the computations, it goes from like a topic that it's like within its category system, I think. But you can just do this since this is a unit of action. The unit of action is joule seconds. You're literally just dividing that by its unit to get out the magnitude of h bar. This is a mass unit divided by a mass unit. So those units cancel out. So this ends up being dimensionless. This ends up being dimensionless. All right. There we go. We've got another thing. All right. Where else do we go here? Okay. So one of the reasons why I showed that magnitude is we're going to do a little bit more wizardry here. We normally have c squared, but as I've learned from Thad, Rick, and John Williamson, A be at peace, is that looking at things inverted or upside down sometimes make a difference. So let's do our friend c squared over here. So we're going to do 1 over c squared. Okay. I was going back and forth over the notation because you can just do Planck length over Planck time and everything. But we did this to literally show that you get these units here. Well, it's better if we share with the class. Go over here. Oh, no, I'm in the way over there. All right. So we'll just do this. All right. So we won't share with everybody. Okay. Here we go. All right. So the stuff we were going over. All right. So our first thingy over there, that elementary charge over Planck charge squared. So basically that guy at the top there. We have this over here. Literally elementary charge divided by Planck charge. We throw in our protective back brackets. We square the whole dang thing. And then we get out this number where we were to just look. Remember, trust but verify. Structure constant. All right. Remember the number that we had. Oh, look, that looks suspiciously like this number right here. I don't know. Let's see. Is that the same number? Something that. Oh, hold on. Let's copy it. Let's subtract them. Okay. It gives us 0. It's the same number. All right. See, we can science. We can use the math that we learned in elementary, middle, and some high school stuff. And we can actually, basically, if you understand those concepts, the computer will do a lot of the tedious doing this, and this. I'm not saying we shouldn't teach it, but I'm just saying if we have computers to do a lot of the more tedious things, that's kind of why Stephen Wolfram built this stuff. So, all right, if we go back. All right. So our second calculation that we had showed up there is, this is basically, we'll take out, let's actually just put in like mass. That's its for 7 digits there. We code out a Planck mass. All right. So, all right. So the second thingy that we have up there. All right. So we got that. Okay. So this is the first version of what I had shown over there. I just erased this. What we did is we did the Planck mass and we put it over what we're going to solve for. Basically, we're putting it over the Higgs mass. We're squaring it, and we're going to claim that's the magnitude of h bar. So I wrote out like this, okay, and then it gives you this over here. And again, it has 2 answers because remember, it's a squared answer. Squaring an answer. If you do x squared, what do we usually get? A parabola. So the reason I chose this convention over here that we can see is h bar over joule seconds equals the Higgs mass divided by the Planck mass, that whole dang thing squared. We have that. The reason why we did that is, let's go back. Let's go to our next tab. Okay. So we did the same thing where, okay, that's squared, and we have h bar over per joule second. Ah, it gives us the parabola. So we can see where it actually comes down. The base is at 0, and it gives us the negative version of the of the Higgs boson, and the positive uh, solution to the Higgs boson. So that's why this convention, we could probably do this for other things. Now, does the negative thing actually have it? I mean, it comes out from this math. I could always say the magnitude, or we could just invoke some positive mass energy conjecture or something. I believe those exist. Um, but I'm just showing that this gives us the same answer, and we can at least visually see why now. So I thought that was pretty cool. So that's why I wrote it that way. Okay, so we have that guy. Okay, and the 1 over c squared, what do we do? Uh, Hold on. I'm skipping ahead there. We're, we're trying to, we're ultimately going to claim, or at least display evidence for what I would claim is the estimated mass in our realm or universe, so to speak. Um, Like Rick's maybe a little bit more agnostic, and that's probably fair because we know there can be some transformation and stuff. We know there's a lot more. And heck, the vacuum's got like a couple, like another magnitude or so times the mass energy in it. Um, we can get to that calculation perhaps either later if we have time or another day. Okay, so what am I talking about? We have 1 over c squared. Let me actually find it before I jump ahead. Here we go. Okay, so we could. I'll do it that way. We'll do it that way. Okay. So you could express it this way. Let me bring it back. Present. Here we go. Here with the class. Okay, here we go. You could express this Planck length divided by Planck time. You could square it. You do 1 over this. And you get this number. And again, the dimensions didn't particularly match. We covered this a little bit the other day. But when you get the same first several digits and the correct magnitude of a friend you have, um, it might be telling us something. Or maybe we could infer, again, we could be wrong. We're probably wrong, but at least when the math works us out, that gives us increased confidence. No? Okay. So as we can see, that's just the inverse of speed squared. 1.1 times 10 to the minus 17. That's second squared per meter. What the heck am I saying? What I'm saying is if you do joule over c squared, oh, what's this? What's this? Oh, so the unit of energy divided by c squared gives us our mass. Oh, look, E equals mc squared right there. And we get the same number, the 1.113 times 10 to the minus 17, and we get the kilograms out because we remove the energy component. So essentially, the c squared scalar operates in units of mass energy equivalents of 1 joule, or at least for its one reference point. That's what we're looking for. We're looking for ones in the system, whether it's a boundary like a Planckian boundary, the Planck time, length, charge, mass, or temperature. Perhaps it's, I don't know, maybe the second, the meter, the coulomb, the kilogram, the Kelvin. Those are ones given our convention. But given our convention, and if these are constants in nature, and we do have high confidence, and then that there's something to them, well, there should be something to them. Okay, so let me go back to the board and I'll finish writing this guy. So that's just, we need to write it this way. It's of the magnitude because it has the correct magnitude. It's just not the right dimensions. So this is the reason why I'm doing this. So and then we do joule over the squared. And again, you could do uh, length divided by time. Oh, actually, no, we don't need that. We just need our normal brackets because, no, did we do that? Yeah, joule over c squared will be mass. Okay, so yeah, we would need to do that because it gives us the mass equivalent. There we go. Okay. Well, that's of the magnitude. Okay, so these are just things to keep in mind. Oh, you just have a 1 and then you have a 1 in the system. Yes. Yes, we do. This gives the same magnitude based upon what you're putting in for your mass element, or at least for every element, it's going to be of this magnitude. I think these are things that are worth thinking about. Don't worry. We're going to get to it. Okay. So I got that. Okay. So we're gonna get to more of the meaty and some of the new part. A lot of this, it's okay, it's been covered before. Let's get into stuff that has not been publicly shared. Okay. And to do this, we're gonna have to go back to the time of Dr. Salvatore Pius started making the scientific podcast talk circuit. Yes. He was talking about the super force, which is just the Planck force there. And he's saying if you set up an equation in a way, and basically the Planck force seems to be a constant given the mass, energy, density, and stuff and things of our observable universe. Okay. This is the thing I had to go back and actually find the old notebook where I still had that equivalence because it wasn't in some of my other things. Okay, so that's that guy. Okay. So the whole thing, actually, we can go to that video. Let's do that first. So we'll go to, where is it? It's on this channel. Yes. Oh, yes, my own channel. Derp. Okay. Uh, Down the tour. Believes. Yes. Okay. This is the one. It's when memes is it? Here we go. Means Steelman's Dr. Salvatore Pius. Okay, so we start talking about some different stuff and things. Let's go.
See, I'm lost for words at times. So come on, someone help
Yeah,
me.
Memes here has a question. He's been very
Jeremiah,
patient the
what am I
whole
looking
time.
for? What's the word I'm looking for?
Okay, so basically
the
we went
radius
on to
of the
this.
observable universe as we know.
So he's going, okay, so he has this equation right here. I'm looking at this. I'm all confused. I'm like, wait, what is he doing? And then I remembered I actually had the notebook. Okay, so what did the notebook actually say? I need to reshare because I just wanted to be a narcissist and just show that for a moment. Okay, so we'll go back to the actual window tab, and it should be this guy. Okay, so the claim is the Planck force, you can set it into, into this equation right here. All right. The Planck force is equal to the mass of the universe times c squared over the radius of said universe. Okay. Now, what is that? That's meter squared divided by length. Because if we're going to assume there's some inversion going on, the Planck length is the minimum unit of length. You can do this little magical transformation. We'll just go to another window, and here's what you do. You just do meters squared over Planck length, and this gives you the inverse of the Planck length in the same dimensions as the Planck length. There's a reason I'm showing those magnitude things. We're building up evidence. Is this a slam dunk case? No. But we're bolstering our priors, or at least attempting to. But I'm slightly afraid that there's some other calculations where I'm like, I need to reach out to Dr. Pius and ask him his opinion on this. But I know he has a bunch of NDAs. I don't want him to violate any NDAs or feel awkward about it. Let's see. I'll go on the panel. That's if I happen to be invited. I think I went on. There was somebody from the Greater Toe community and Theories of Nothing community. We did like an hour something interview a few weeks ago. It should be getting published. He said around this time, like at the end of the year. If I see it, I can share it or something. It was quite ontological, I think. But no, a lot of folks are busy and everything. So it's like, all right, I might as well share some stuff, get some ideas out there, work some way into the algorithm, maybe get monetized at some point. Shout out to my patrons. Uh, Joe Franco, Dave, and Dan. Thank you, my friends. Help keep the lights on. But okay, so we have this thingy here. So what's this? It's just meters squared over the Planck length. All right. It gives us, so the claim is if we have some hypersphere in which we live, let's say like a 3+1 or a 4-dimensional hypersphere that seems to work with the maths and everything, you get a radius of like 6 times 10 to the 34 meters. It's freaking ginormous. How ginormous is that? Yeah, it's about 7 or 8 magnitudes the diameter of the observable universe. That seems to make, I don't know, things would probably look pretty flat, no? We're going to need probably another few magnitudes to start to get noticeable curvature. Okay. So we got that. Okay. So that's basically the claim. That's this thingy down here, that meter squared over the Planck length. So the claim is we set the Planck force equal to, we're going to solve for x, the mass of universe, I claim, or our realm of persistence, times c squared divided by the radius we're going to claim from that number of the universe. Okay. So what do we get? We get this familiar number that, remember this magnitude, 1.45 times 10 to the minus 18. It's coming back. It's coming back in a fantastical way. Okay. It gives us this phenomenally ginormous number. What is this ginormous number? All right. So we're solving for kilograms. So I got the number. Throw in kilograms. All right. So I can't count that many things, but it's expressed in grams as, okay, they're rounding up. See, it's 8331, and we'll put the 5 there. because that's 8. They're rounding up because the next digit is a 5. Okay. So what we're going to do is we're just going to take this. We're going to go down 3 orders of magnitude because, well, it's a kilogram, so it's 1,000 grams. So, all right, kg, 1.5. Okay. So we're going to take this number here. What's this number here? All right, so 8.3 times 10 to the 61 kilograms is the estimated mass of universe, I will claim. All right, so that's about 8 orders of magnitude more mass of ordinary matter than our observable universe. That was pretty close to that magnitude. It was a little under 8 orders of magnitude, and we got a little bit of a buffer there. Oh, very interesting. Okay. So let's write that guy down. All right. So you got that guy. So it's force Planck. All right. So the claim is we take the Planck force. We're gonna do F. So P, you can set that equal to mass of universe. God, what a freaking grandiose claim. I feel almost embarrassed even just putting this up here, but it leads to phenomenal, crazy calculations. Oh God, and the light is in the way. Maybe that's fitting. Okay, we'll move in a second. All right, so mass of the universe times c squared. Let's see a little bit over here, just c squared, and then we have meters squared over Planck length. So we'll just do meters over L sub p. We bracket them up meters squared, pardon. And that'll give us out a dimensional quantity, because otherwise, if it's just a length and a length, the length cancels out, and then it just gives us a dimensionless thing. And occasionally we just do magnitudes over there to make our lives easier. Okay. So we've got this. Okay. So it gives us that crazy number, that 8 times 10 to the 61 kilograms, about 8 orders of magnitude greater than the stuff we have there. Okay. So, and let's actually put what it comes out to be. I'll do an actual calculation thing here. That is equal to, you're going to see why, 8.331 times 10 to the 61 kilograms. Okay. There's a reason I am writing it out. I think you guys are going to like this. Okay. So let me just skip ahead to see why. Okay, so we got our kilograms there. Okay. So whilst doing a number of calculations, this is a fun thing. Whilst doing a number of calculations, I came across something, and you didn't quite finish it. It's like, all right, I see this thing. It's like, all right, I'm looking at these things. I look at this thing, and I'm like, I think I know exactly what I need to do for this, but I haven't done it yet, just because I know what Rick's frequencies chats, and Rick's done. We've basically been looking at a lot of other stuff. Rick's been looking at the architecture. I'm like, Rick's got gravity covered. So I'm like, all right. Well, I found all these things. So when you do that meter squared over, actually, let's do that. So the claim is, we should probably add a little bit more context. So the claim is, if let's do radius uni. Okay, so radius and first claim is equal to meters squared over Planck length. Okay, put brackets on because they make me feel better about myself in case I make an error. Just compartmentalizing things. Okay, so if that's claimed as the radius of the universe, then we got that. So it's like Oh, I can just erase that. There we go. Let's make the notation tighter. If we're going to explain ourselves right next to it, so we're just going to do, all right, our universe. Oh, yes, it is our universe. Yay! God, Master Splinter is rolling around in his grave. Unless he's still alive in whatever current Ninja Turtles verse. Okay. Oh, and this, while we're writing stuff down, let's do this. This is, what's the meters over? 6.187. 6.187. 6.187 times 10 to the 34 meters. Okay. And again, that's meters, so that's a length. If it was squared, it would be an area. If it was cubed, it would be a volume. We're building up to something. We're building up to something. I know it's taken over half the show, but we will get there, my friends. Okay. Hold on, I'm gonna need a coffee for this. So, not so long ago, Physics Monastery, we had our little fall gathering, a little conference, if you would. A bunch of folks come out from all over. Different things were shared, things were learned, stuff and things happened. Okay. A short time after that, I, along with Casey, decided to go on a road trip. That's right. I got into a vehicle with a gangster mathematician, and we went out to the great land of Portland. We spent some time there, and we went to go up to visit my stepbrother and a particular mad scientist. Yes, a mad scientist. I see you there, K-Shell. Don't worry, you're here for the good part of the story. So, well, we went up to Seattle because number one, my stepbrother has been inviting me out there for years, and I'm like, I'll get to it. I'll get to it. All right. So eventually, it's like Rick's like, oh, he lives a little out of Seattle. It's like, all right, how about we make a journey? Let's go meet a mad scientist because we can. So we went on the trip. We went up from Portland to Seattle. And don't get me wrong, the West Coast there's a lot of beautiful stuff out there. I see why people like it. But all right, we eventually met a mad scientist. And then, oh, hold on, I think we actually have pictures from the day. So we had the first annual, I think, Rick the WIT conference or whatever it was up there. All right, no, these are the Vegas guys. Hold on, I have the other guys maybe over here. Where did I have it? Maybe this notebook. Okay, but essentially, we had a number of different discussions, and then I'll put it. Okay. All right, we're wasting excess time. All right. So long story short, I think the second before the final day before we went back, we went out to the aquarium. Why? Because Seattle has a great aquarium. Boston has a great aquarium. I always liked the aquariums, and you get to see literal dinosaurs floating on by. But eventually, we grabbed some food. Fish and chips were good and everything. But eventually, we got outside and we were chatting. We were getting ready to part ways, and we were sharing a couple of things, some calculations. People were saying all different words. I had been without sleep for a number of reasons for a little while, and eventually I asked, I'm like, oh, Rick, you've done a bunch of these calculations using that hypersphere or basically this operator, because when you multiply it by different things, you get very interesting results that seem to line up with a lot of different Planckian things you'll get, because a lot of times you hear about, Planck's constant or the reduced Planck's constant, H bar, and you'll hear that, and then you'll hear the Planck length, the Planck time, the Planck energy, Planck this, Planck that. Then you'll have different folks like Dr. Salvatore Bias, Rick DeWitt. They both brought up the Planck force. I'm like, okay, that's very interesting. And then there are lesser known Planckian things. You got the Planck power. You got the Planck frequency. You got the Planck density, the Planck pressure, the Planck intensity. What is that? Watts squared or something like that per steradian. I'm sure that's wrong, but it's yep, the Planck spring constant. That's one you don't really hear about. Why? I don't know. I guess it's not used a lot of time in the literature. Maybe it's not as sexy as c squared. Uh, Maybe just because we can write that E equals MC squared. That's a reason I'm putting these things on the board, because I feel like, all right, if we actually have some of these things, you can just look at it and be like, oh, so all that fancy notation, you're just saying this? Okay. Not everybody always is very as eloquent to say this is that thing. You're just like, that's just a bunch of jumbled symbolism. I don't know what that means. Okay. That's what happened to me. That was my personal experience. And then you need to immerse yourself and try to learn the language. And there's still lots of stuff. Most things I don't understand, but we're trying to be less wrong. Why? Because that's the quest of science, to be less incorrect, I claim. All right. So that tangent aside, basically, I done a number of calculations. And then I looked into a mad scientist's face and I was like, I keep getting this one calculation that I'm just unsure of. A lot of it is I just hadn't finished it. And I'm like, it's like 1.45 or something times 10 to the minus 18. And I'm just not sure what to make of that. And anybody that's ever met Rick, he's a fairly jolly fellow. The retired programmer, he speaks with a very specific specificity. He also has the worst poker face in the world. Because I just said that, and the look on his face, we're literally outside the aquariums by the pier in downtown Seattle. It looked like he just wanted to run up to the railing and do his whole Leonardo DiCaprio, I'm the king of the world, and scream the answer out among everyone there. He did not say anything, but the look on his face was enough for me to say, okay, I think I know exactly what it is. Okay. Yeah, long story, basically, G in the Planck, big G in the Planck mass. But as we got back and I was looking at the relationship, Thad did standard Thad magic, and a very interesting thing I'm going to claim. Okay, so the claim is for this guy, you set the Planck force equal to this relationship. The mass of the universe, or aka the mass energy of the universe, because we're squaring it, divided by the radius of the universe. So basically, if you have this and you set this, you're basically just solving for x here. We're just doing the same thing that we did over here. We have like something that we have to an approximation. We're like, all right, well, let's just solve for x because it seems to get the first 3 digits, and we only have about 3 digits, significant digits of confidence in the mass of the Higgs. So it doesn't seem like the most unreasonable thing to do. Maybe I just need to add more dimensions to that. Maybe that would make some people happy. I kid slightly. Okay. But the reason why we have that is, okay, that gives us this number here. All right. So the interesting thing is, we need the correct marker. There we go. Okay. So this is, this is going to be fun. This is going to be fun. Okay. So that guy, or no, it's that guy. All right. So coincidentally, if we take the mass, we need to do blue. Keep our convention going. Like you go, looking like this. If we take the claimed massive universe, we divide it by the Planck mass, that is equal to meters over the Planck length squared. That looks very pretty. I'm just saying. Wait a second. Wait a second. How do you do it? That's why I started off with the Arthur C. Clarke quote. I realized you should do probably the keywords, but I'm like, any sufficiently advanced technology is indistinguishable from magic. I don't know about you all, but this looks like freaking magic to me. And the one thing, we don't have a measurement for the mass of the universe, but that's why if we use this little ad hoc thing and we assume that there was something there, and the Planck force ends up being something we could use as whether it's, well, does force have an inherent direction? Because I want to say the word scalar, but you can't use scalar if there actually is a vector, if there actually is a direction to it. But if you could use that as a constant to help, maybe not as a scalar, but as a scale factor, I don't know. That's probably not the same thing. But basically, wait a second. So what you're saying is, and again, meters is out here because this is a mass term, this is a mass term that cancels out, becomes dimensionless. This is a length term, this is a length term. We square the whole dang thing. Wait, hold on. What you're saying is the mass of the universe divided by the Planck mass is equal to the magnitude of meters divided by the Planck length, the whole thing squared. But we're just doing the same thing that we are over there. There's no way that can be possible. Unless that is an accurate thing. The reason why we show that is because if we do this calculation in purple, we get, at least for like the first 7 or so digits, because each Planck unit and stuff has its convention for so many digits and everything. But at least for, like, I think the first 6 or 7 digits there, it ends up being the same as this number. 8.331 times 10 to the 61 kilograms for universe. It's a crazy thing to say, but I just think it's, I don't know. I don't see a lot of people talking about this. This is stuff that we can literally just go into Wolfram Alpha, and let's do that right now. All right. Here we are. Shorthand, yes, it is. It is shorthand there. Yes, golf clapping. But let's go back to our screen here. Share with the class window. Boom. All right. So we go over here. Okay, so here's our Planck force. That was the first thing we had there to try to estimate if we had information. And again, the other information will need to be verified. I'm just saying that this is shorthand, but I think this is where, at least, and again, I'm very biased on this, where the claim of beauty within physics comes in, is that if you can summarize it into something that is more simple to show the relations. And again, I'm sure there's going to be fancier things and other ways to model this, but I'm like, all right, we're solving this using a graph. Like literally that first guy, we're solving with this graph here. We're literally just plotting information. And that's why algebra is awesome. So it gives us that estimated number right there. And we have this other dude over here. So basically that guy right here, where we have m uni over the Planck mass is equal to meters over the Planck length, and we square the whole dang thing. That's this guy right here, where instead of mass of universe, we're solving for x, because we don't know what the mass of the universe is. We can't measure the whole dang thing, at least right now. So it gives us this interesting thing. For those of you that have maybe done this for a while, that's the inverse of the Planck mass. That's an x, and that's the inverse of the Planck length squared with no units. And again, we're just literally solving for a graph. Okay. Oh, wait a second. That 83315 ginormous number looks a lot like that number, which looks a lot like this number, 8.3315, and then I think it deviates because it goes 499 there, and then this guy is 487. Oh no, it's almost estimating like the 7th or 8th digit. Huh. It's very interesting. And again, I realize it's probably just a computationally reduced thing there, but seeing the relationship just right there, it's like, wait a second. You're you're saying mass of universe divided by the Planck mass is equivalent to just meters over the Planck length, the whole dang thing squared. I'm a little biased. I think that's very pretty, but we're not done. Oh no, my friends, we are not done. All right, so we have that. Okay, here's where okay, so this is the stuff I really am excited about. Okay, let's get into some real wizardry here. Okay, we've got those dudes. Let's continue. So we've got those things with my blue markers here. All right. So if we happen to take this dude over here, M uni. So if we did S universe, and we divide it by what's another one of those Planck things? Oh wait, the density. I'm not going to write dp here just because I realize I wrote it on the thing there, but it's let's do Planck density. Okay, so if you do this, you end up finding that that is equivalent to the magnitude of the Planck length in meters cubed. Wait a second. What just happened here? Wait. So if we take this m here, this claimed mass of the universe, and we divide it into the Planck density, we get the magnitude. It's 1.6 1.616 or whatever the rounding, 1.6 times 10 to the minus 35 meters cubed. That's very interesting. We get the guy. All right, so that's equal to 1.616 times 10 to the minus 35. But instead of a length, it's a volume. It's the Planck length in volume. It's right a little bit off of the Compton radius of an electron when you take the cube root to actually find out what the length is. That's again a tale for another time. Needs to be investigated further. That's meters cubed. Okay, well that seemed to be very interesting. All right, now this leads to other questions since we've been playing along so far. Is once we get over here, okay, we had a volume. So what happens if we take? Oh, I need to actually share again. There we go. All right. So what happens if we take the claimed mass of the universe and we multiply it by c squared? That gives us the mass energy of the universe, or at least the mass energy equivalent of the mass in it. It gives us this crazy number right here. Okay. So if we take that number, well, don't worry, not going away just yet. Do this guy. So if we do that, and then let's do it over here. All right, so if we do mass of universe c squared. Now, there's a reason we're going to take that. So we're taking the mass energy equivalent, and well, we got a mass energy equivalent. Maybe we should divide it by something. What could we divide it by? How about another Planck thing? How about the Planck pressure? Okay. We take that, we divide it by the Planck pressure. What do we get? Oh, look, we get the same dang number. 1.616 times 10 to the minus 35 meters cubed. Wait a second. Isn't that like that vacuum catastrophe thingy? Where it's like the estimated energy of the vacuum. So you take the Planck mass and you divide it by the Planck volume and you get the Planck pressure. It's about 10 to the 113 pascals, units of pressure. Huh. That's a very interesting thing. But you divide this guy because we just found the energy equivalent of that. And when you do the dimension things, it just cancels out. And that's over the Planck pressure. Under pressure. All right, there we go. And bracket equals, again, the same thing. LP, magnitude of LP in meters cubed. And then write it over here because it's the same dang thing. So I don't know. Are we seeing a little pattern? Now, again, maybe that shouldn't be surprising just because of standard dimensional stuff and things. But okay, it was the process, or at least the process that I went through. If it had to torture me, well, I'm trying not to torture as much. But this is how you learn. You gotta do things not because they're easy, but because they're hard, yada yada, stuff like that. Meters cubed. Okay. Well, let's get to a bit of a punchline, shall we? Okay. We've looked at some of the stuff. All right. Let's wrap up with a little stuff. So Thad had mentioned the Planck spring constant. What the heck is the Planck spring constant? Okay. Coincidentally, it's a mass divided by time squared. Wait a second. This number looks familiar. 7.488 times 10 to the 78. Where have I seen that before? Huh. Well, it was right around. Wait a second. Slightly different dimensions, but if we take the claimed mass of the universe and we multiply it by c squared, we get 7.488 times 10 to the 78 joules, because that's energy. Wait a second. Wait. Hold on. Wait. Okay. So let's write this down. All right. Let's actually embiggen the screen. All right. So we're embiggened again. We got that. So the claim is if we take, all right. So we do this. We do the mass energy. Let's do the spring constant. Okay. The Planck spring constant is Planck mass. Okay. Planck length. LP over time Planck. You square it equals 7.488 times 10 to the 78 newtons. Joules. We'll do joules because that's what we've been doing. Joules. Okay. And this is the Planck spring constant. Okay. Okay. Why am I calling it the Planck spring constant? Because that's what you get. Okay. Now, if you take the mass of the universe, all right, so and it's still crazy. Universe. All right, c squared. Okay, and then we divide it by the Planck spring constant. ring constant. Okay, we take that. That is equal to 1 meter squared. I was not expecting that. Maybe I should have. And again, just using our basis of convention here, it's like, forget. Yeah. Oh. Oh. Oh, okay. Well, I guess that makes sense. You can just do it standard thing and then just multiply by meters squared. Don't that just beat all? Hold on, I'm on the wrong side. There we go. But okay, so that whole thing there. Let's actually show it. Okay. So here's the thing. All right. So we got our estimated again, claimed mass of our realm, mass of the universe, or whatever you want to say. It's mass energy equivalent of that. 7.4 times 10 to the 78. All right. And that many joules, because that's energy. All right. And then if we do that spring constant, that's, I just keep on reading it as like kips and stuff like that. It's the spring constant. That's what it says. Mass divided by time squared. Okay. We get the same magnitude. We do the calculation. We put that stuff up there. We divide it by that stuff. It gives us this. All right. Claimed mass of the universe times c squared. E equals mc squared to get our energy equivalent of mass in universe, whatever that means. We divide it by the Planck spring constant there. That mass divided by time squared. We get 1 meter squared. If you do it the other way, you get 1 inverse meter squared. Or inverse meters squared. So yeah, that's why it's like, okay, I first did like the Planck. No, that's why we want a coherent thing. So it's like, all right. So again, you do that Planck force calculation. It's like, all right, it seems to get it pretty well for what we're measuring and everything there. But it's like, what do you have to reference it by? It's like, okay, well, if we do that, and then we divide that thingy by the Planck mass, and it happens to be of the magnitude of meters over the Planck length squared. That's very suggestive. And then when you do that claimed mass of universe divided by the Planck density, you get the Planck length in meters, like times meters squared. You do the, oh God, I forgot the E. There we go. You do that, the mass energy, and you divide by the Planck pressure, which was, at least according to, I believe, quantum mechanics, or at least the standard model, is supposed to be, that's what people herald as, oh, it's the worst calculation. But what were people actually calculating? All they did was take the Planck mass divided by the Planck length, and they got a ginormous number. Why? Because the Planck mass is a heck of a lot bigger than all the other Planck constants, with the exception of the Planck temperature, or at least the 5 base units. That, and the Planck time is basically the actual smallest. You divide it by that, you get a ginormous number, 10 to 113 magnitude. Okay. So, but they were thinking that's going to be every Planck volume within the vacuum itself. Yeah, if it did that, I think we all would have exploded by now. Or things wouldn't be as it seems. However, if you were to take the mass energy, or at least I would claim a conjecture, the total mass in its energy form, and you divide it by that unit, you happen to get out Planck length times 1 meter squared. Now, if you were to take that, yes, you would have the Planck pressure at that point. Now, I'm thinking that's a lot of pressure. Maybe it would try to lessen the pressure. Maybe it would look like it would, I don't know, look like a cosmic kablooey, a big bang. Maybe something like that. Maybe something different. I don't know. Can't say I wasn't there. But just We'll just wrap up and we'll get a little bit closer. Yes, so you can see some more stuff. Okay. So what was the whole point of this? The whole point of this was to just show that we can, at least computationally, literally putting it into a computer, reduce the amount of effort. Because as we've said before, the alpha is normally defined as elementary charge squared, all divided by 4 pi c h bar epsilon naught. Thank you, Rick, for the correction. I've been saying E naught for a while. It's technically epsilon, the electric permittivity of space. Okay. Then you realize you can coordinate. So alpha equals elementary charge over Planck charge. Protect the bracket, square the whole dang thing. Okay. So we have our PB and J conjecture here. All right, what's that? It's that H bar divided by joule seconds. So the elementary unit of action divided by the 1 of units of action equals the mass of the Higgs divided by the Planck mass squared. Okay, and then we notice this 1 over the magnitude of c squared. One of the core tenets of E equals mc squared. And again, there's more to that, but in the simplest reference frame, assuming non-moving stuff, but if that's another bag of worms. But we got 1 over c squared. The magnitude of that is equal to the magnitude of 1 joule over c squared. And again, maybe that's just an obvious thing. Don't hear a lot of people talk about this. So I think it's very important, or at least to look at what the ones might be. Okay. So then we got up to here, where it's like, all right, according to the current measurements of the mass of the observable universe, the radius of the observable universe, this with or without a factor of 8 pi seems to, yes, okay, yes. Oh, we're like a magnitude or so off. It's like, all right, seeing as we have no idea how big things are, being in the ballpark, so to speak, maybe a very large ballpark, ain't that bad. But if the Planck force is equal to the mass of the universe times c squared over the radius of the universe, according to at least these calculations, it's about 8 times 10 to the 61 kilograms if we're looking for the mass of the universe. Okay. What's the radius of the universe? I claim it's probably, what's that is conjectured, we're seeing an inversion. Well, what's that inversion? We're taking meters squared over the Planck length. Gives us 6 times 10 to the 34 meters, or basically the inverse, the Planck mass times 1 meter squared. Okay, the estimated radius. What do we have over here? All right. Thanks to Rick's befuddled expression that told me everything I needed to know, I came back, did some calculations. Thad did wizardry, like Thad does, of, wait a second, it appears that the mass of universe, whatever that is, divided by the Planck mass boundary is equal to meters divided by the Planck length boundary squared. Look at our length all getting squared. I don't know what's going on. Then we get down to this, where it's like, wait a second. It seems the claimed mass of the universe divided by the Planck density, which is like a 10 to the 96 number. Why the heck is that a thing? Well, maybe that's why it's a thing, because it comes out to the Planck length times meter squared. Okay. And then if we take the vacuum catastrophe, is it really a catastrophe, or just simply a misinterpretation by some folks that if you just take the mass energy of universe, you divide it by the Planck pressure because it's under pressure, we get down to the Planck length times meters squared. It's a very interesting. And then we just wrap up over here. If we take the lesser known Planck constants, like the Planck spring constant, which, hey man, I don't make the rules. I'm just saying that this is what comes up. Take the Planck mass times c squared, blah, blah, blah. We get 7 times 10 to the 78 joules of energy. That's a lot of energy. But if we take that and we divide it into the mass energy of the universe, we get out 1 meter squared. Links are in the doobly-doo, of course. Feel free to trust, verify, refute. Let me know what you think down We're going to be wrapping up now, but any other comments below? If all of a sudden you're like, memes, you're totally wrong, feel free to spread the information around, to interact however you would like there. I ain't the boss of anybody, but let's see what we got for other stuff and things. Let's see. So Thomas posts like, yeah, a lot of people do post a lot of old content and just reshare things. My thing is just give attribution. Oh yeah, since I told a story about Rick's presentation, Archimedes' law of gravity is in the doobly-doo below. It's very interesting. I suggest they submit it to New Scientist because it sounds like something that's up their alley. Hey, WWKK. Good to see y'all. We've gone over the time limit, but that's all for now. Take care of yourselves, everyone. It's a crazy world out there, but it's hoping 2025 will be a surprise. Hopefully for the better.